Welcome back to this course on algebraic geometry and commutative algebra. In last many lectures we have been only doing algebra. Today I want to switch back to geometry and prepare for proving the cornerstone of algebraic geometry and commutative algebra, which is known as Hilbert's Null-Stellen-Zatz. So let us recall the setup, because some of the things one might have forgotten. So our setup was, I have a field extension L over K, field extension, and we have defined, and also let us denote k x1 to xn. This is the polynomial ring over the smaller field in n variables. So this is a polynomial algebra over k in n indeterminates x1 to xn. And for any ideal, we have noted, we have defined for any ideal A. Let us abbreviate this polynomial algebra by R. So for any ideal A in R, we have associated a subset of L power n. So that subset I have called it VLA. This is by definition all those tuples x, small x, x1 to xn in L power n, such that f of small x is 0 for all f in the ideal A. And this we have called it K algebraic set, K algebraic subset. Of course, this is in L power n. So sometimes I will also call it affine. Let me put that in a bracket. And also we have noted that this algebraic K algebraic set does depend only on the radical of the ideal A. So that I will denote the set of radical ideals by IR. R, IR, this is the set of all radical ideals in R. So that in the notation, that is all those A ideals such that root of A equal to A. Also note that we have also proved that to define this algebraic K algebraic set, we need only to look at the finitely many polynomials, because we have proved by Hilbert's basis theorem, HBT. This is abbreviated for Hilbert's basis theorem, that every ideal in the polynomial algebra is finitely generated. So A is generated by F1 to Fm for some F1 to Fm in R, and therefore the zero set of A in L is precisely the intersection from I1 to M VL of Fj's. So we have to study only finite Limini polynomials and their common zeros, and that is the central theme in algebraic geometry. Alright, so with this we have defined a map VL. This map, think of this as a map from R ideals in R, radical ideals in R, to what is called K algebraic sets, This is a subset of the power set of L power n, and this map is any radical ideal A going to VL of A, and we want to study this map. In particularly, we would like to give necessary conditions so that this map is bijective. So that is what we are looking for, conditions so that this map is bijective, and that will allow us to study geometry, that is geometric study of the K algebraic sets with the algebraic study of ideals in the polynomial algebra. Alright, so I just have to recall here that on this algebraic sets we have defined on Ln. So also this is what we have recalled. Another thing I want to recall here, recall that on Ln we have defined a topology what is called Zariski topology. By declaring the closed sets, and the closed sets are precisely the K algebraic sets, by defining closed subsets which are precisely K algebraic sets. And with that we have a topological space. So we can talk about topology, continuity, continuous maps, and open sets, closed sets, properties of the topology like compactness, connectedness, and so on. And this interplay between this topological space and the ideals in the polynomial ring is a central theme of studying in study algebraic geometry. And what we are set up, this will be a classical algebraic geometry, but then later on I will also say more about this more general situation where things will be easier to prove, but the setup will be little bit more abstract, and our aim is to really play both ways, not only from going from ideals to the algebraic sets, but also the conversely. And for this we will have to define the map in the other direction, and we will look for when is it an inverse for this map. So that also already we have defined. So let me recall that definition. Recall also that we have also defined the map from that map is called IK. IK is the map from the power set of L power n to the radical ideals in R again, R is the polynomial ring over K. So what is the map? Take any subset Y and associate this to Y. You consider the ideal IKY. This is by definition all those polynomials f in R. Remember R is kx1 to xn such that this polynomial should vanish on every element of y. So f of y is 0 for every y in y. So first of all note that this Iy is nothing but it's a intersection of all those, this is intersection is over y in y such that it is intersection of IKY. So that means first of all note that each one of these is a radical ideal, because if power somebody vanishes at y, then f also vanishes at y, because we are taking the images. So we are working in the field L, therefore this is a radical ideal in R, because we have taken only polynomials in R. So we do have a map from power set of Ln to y, and this map obviously I will list some obvious properties without proof, or some of them we would have also proved earlier. So first of all both these maps, so some obvious properties are: one, that VL of empty set equal to VL of 0. 0 means 0 ideal, so this is also radical ideal. So that is L power n. On 0 everybody on 0 polynomial vanishes at every point in Ln. So this is obvious really, and similarly VL of the whole thing R, which is also same thing as VL of the polynomial 1, which is equal to empty set. So this means both these means empty set and Ln are closed sets in L power n in the Zariski topology. Okay, what are the counter properties for? So that I will write it 2. So whenever I list properties for VL, I will also list properties for IK. So IK of empty set is a subset of L power n. So this is the whole R, and IK of L power n, this is equal to 0 if L is infinite. This I would have checked earlier, so I will say check this. Either we have explicitly proved earlier lectures, it's for a while now we have not come to geometry, so I would say check on this. If I have not checked it, please verify this. This is very easy to verify this. Infinite is very important. So I should tell you what happens finite. So on the other hand, for example, if IK of, what is IK of K power n? K power n is also subset of L power n. So this is equal to ideal generated by x1 power q minus x1 so on xn power q minus xn. This is when if this equality holds, if K is a finite field with cardinality Q. This is also easy to check. I will not check this. This I would put it as an exercise. Alright, so I would also like to recall that what are the cases of these field extensions we will be interested in. So, the cases of interest, typically we are interested in the field extension where the upper field L is algebraically closed. Algebraically closed means we have already recalled this in the first lecture only, that algebraically closed means every non-constant polynomial with coefficients in L has a 0 in L. Typical example of algebraically closed is, for example, L equal to C, complex numbers. This is algebraically closed. This is a very celebrated theorem proved by Gauss. So, this is L. So, we are typically interested in L over K where upper field is algebraically closed. Particularly we are interested in for example we are interested in L equal to algebraic closure of K. So, this is K bar denoted by K bar. We have learnt in a Galois theory course that every field has algebraic closure and it is unique up to K isomorphism. So, we will assume that. So, typically to give specific examples of these pairs are, for example, you can take field extension C over R. C is an algebraic closure of R, or you can take Q bar over Q. This is precisely called arithmetic geometry. Or these days even engineers are interested. So, that is finite field FQ bar over FQ. This is also important for studying this, and so this or K equal to L equal to K and K is algebraically closed. And this is what is classical algebraic geometry. This will lead us to classical algebraic geometry. This will lead us to algebraic geometry, the arithmetic geometry, and this is you can say classical complex analysis and real analysis. All right. So, this is what we keep in mind. Okay. So, so the third property I want to say that VL and IK both are inclusion reversing. That means what? That means VL of a root ideal A and VL of a root ideal B. So, if A is contained in B, then smaller the ideal, bigger the VL, because this is intersection over the smaller set and this is intersection over a bigger set. Similarly, for IK, if y and y prime are two subsets of L prime, L power n, one contained in the other, then ik of y is bigger than ik of y prime. So these are obvious things, there are obvious things, so there is nothing to prove there. Okay, so okay, fourth one is what happens with the composition of ik composed with VL. So this is a map from the root ideals to the K algebraic sets and K algebraic sets to the root ideals. So this is map from root ideals to root ideals. So if I take this on any A is any ideal, in fact ideal in R, then that will contain a root of A. See, remember that VL is not just defined for a root ideal, it is defined for all ideals, but it depends only on the root ideal, but it is defined for any ideal. So this inclusion, only one inclusion, and we are hoping that if I take a root ideal, then it should be equality here. That is our hope, but we will have to keep some assumptions on L and K, this one. So and similarly for the other way I want to write VL compose ik of any subset y let me write not any subset is equal to y, where y for if y is a K algebraic set, subset in L power n. So these again I will not prove, these are very easy to check. For example, if I have to check this, if I take any element here, then so that is a polynomial with coefficients in K. So the power of that will belong to A, and obviously this power will vanish wherever this VL is vanishing. So that means it is in this ik. So this side, remember this side is ik of VL of A, and if you want to check which polynomial should belong here, we have to check that it should vanish on everybody here. That is the definition of I. So if a polynomial is here, the power is in the ideal A, but that power will then vanish for everybody here, because that is the definition of VL, and therefore that polynomial will also vanish on so therefore that polynomial will belong to the ik. So similarly this is also easy. So I will just mark here, check this equality, similarly check this. These are easy checkings. Okay, now the next one, alright, so next one is if fifth, I will write the number fifth, if two algebraic sets, if V1 and V2 are two K algebraic sets, then V1 equal to V2 if and only if ik V1 equal to ik V2. This will immediately follow from the fourth, so I will not say more about it. Okay, so the next one 6, that if I take ik of the union Vi, arbitrary union I in I, and Vi I in I is a family of algebraic K sets, K algebraic sets. Then this union becomes intersection. And what happens to the intersection? The intersection ik of the intersection Vi, this will only contain the ideal, some ideal of Vi's and take the radical of that. So these again I will not check, these are obvious things to check. Alright, the next one now about V. So what is the number I forgot? 7. VL of the intersection, finite intersection, VL of finitely many ideals, I is from 1 to m. This is same thing as VL of the product A1 to AM. Also it is same thing as union of I is from 1 to m, VL of AIs. So this also shows that finite union of K algebraic sets is again K algebraic. Okay, what happens to the intersection now? So intersection, arbitrary intersection, VL of AIs, that is same thing as VL of the sum ideal. Here these AIs are ideals in R. So this shows that arbitrary intersection of K algebraic set is again K algebraic set because it is VL of this ideal. Alright, so that this 7 along with 1, it shows that it forms a topology, and that is a Zariski topology. Alright, so now the last one 8. If I have for any point for every A equal to A1 to An in K power n, which is also a subset of L power n, then we can talk about ik of the singleton set, ik of singleton A. This is precisely the ideal generated by x1 minus A1, xn minus An. Remember that these polynomials, all these linear polynomials have coefficients in K because we are assuming that A1 to An is in K, and this is also we have denoted by m suffix A, which we have noted that it is a maximal ideal in R. So if your point, this point was not in L power n, not in K power n, but it is in L power n, then it is more complicated to describe this ideal of that point. So we have these basic properties which are easy to check. Now I just want to remind your attention to this. So we have checked that this property, this 5, it says that if I have two algebraic sets, then V1 equal to V2 if and only if this. This precisely means that the map IK map is injective, because if IK of V1 equal to IK of V2, then V1 equal to V2. So, this shows that, and V1 V2 are maybe any not necessary algebraic sets, but arbitrary two sets. But so I will note, therefore, this is the number 5. By 5, note that by 5 the map the map IK. IK, I am thinking a map from K algebraic sets. This is the set of all K algebraic sets, which is a subset of P L power n, two radical ideals in R. This map is injective. This is by 5. That is precisely one thing. Okay, so and what is that we want to show? So we will show that. I will write on the next page. We will show that if L is algebraically closed, then IK is bijective. And equalities, which equalities? First of all, remember this IK VL of the ideal A equal to root of A for every ideal A in R. This was listed in one of the property above, and this is one equal one. So there it was this inclusion, but now we will prove that it is equality. And second one is in IK of intersection of Vi's I in I equal to radical ideal of sum of these ideals IK of Vi, where Vi's are K algebraic subsets in L power n. So this equality, there also it was only this inclusion, this IK was bigger than this sum. So this is the main this equality here also, the first equality. So this equality is also known as Hilbert's. So this equality is also known as Hilbert's null Stellen Satz. So Hilbert has proved null is a 0, Stellen is a place, and Satz is a theorem in German. So this is, Hilbert was a German. So these names are, these terms are coming from German. So I just want to give a little bit history and then stop this half. So Hilbert basis theorem HBT, and this is also I will keep calling HNS, and HNS were proved by Hilbert in 1890 and 1893. And this Hilbert-Schnoor-Cellensatz, this is the beginning of algebraic geometry, beginning of modern algebraic geometry. And he this HBT, as I said earlier also, this was proved by Hilbert to prove some invariants of some existence of some invariants. This was also very important at that time, and that was the reason he proved that. In the next half I will try to prove Hilbert-Schnoor-Cellensatz, that is, I will try to prove this equality, and there are various forms of this Schnoor-Cellensatz, and this appears to be the strongest one, but I will state many forms, many different incarnations of this Hilbert-Schnoor-Cellensatz and prove that all of them are equivalent. So, I stop here and we will resume after a break for the next half. Thank you.